So we were looking at these different types of correlation. So if you look at this correlation, what you are noticing is the fact that it is a positive one correlation, which means when your x is increasing, your y is increasing. So it is a positive one, and it is a very strong correlation because the maximum value a correlation coefficient can have is a positive one. If you look at this one, is you are seeing is when your x is increasing, your y is decreasing. So this is where the high low and the low high comes in. Is x is increasing, your y is decreasing, and it's a negative one correlation, but it is a very high correlation because the maximum value on the left hand side that a coefficient correlation can have is a -1. 0.6 is a moderate correlation, but this is a positive correlation because when both x is increasing, y is increasing. But here again, when x is increasing, y is decreasing. Scatter plots are very important, and research actually recommends for you to plot scatter plot, to do actually scatter plots to look at the spread of your data before you do any statistics on it. And we will talk about outliers and other things also. The research that gets accepted does do the scatter plots, and then they work on the other statistics. Here you can see the spread is all around. There is no defined spread, so it is a zero. The correlation coefficient is 0. R is, if I have not said this before, R is your representation or symbol for correlation coefficient. So what are the scatter plots? They are a visual representation of a data. Is there anything else we would like to know about it? So like if you say that it is a 0.8 correlation, I may want to know something else about the data, and that is where I will go further with it. The R value is the correlation coefficient, and then we also have a significance value. So in the one that I just talked about in this slide, in over here where it was 0.8, and I could take any value, but you have to, so P is greater than 0.001. We'll talk about this as we go forward, but what you really need to see is the R square. R square is actually called it is the proportion of variability. So when I square the correlation coefficient, it exaggerates the relationships, and it helps you provide a better way of stating your results. So if your correlation coefficient is 0.5 and I square it, it would give me a 0.25 and then multiply by 100, so that is 25%. So I could say that there is 25% of the variance in one variable can be explained in the other variables, which means that they are related by 25%. So think about it, that if it is actually 0.8 and I square it and I get like 64%. So if more than 50% of the variance in one is explained by the variance in other, that means they are pretty strongly correlated to each other. 100% is explained, then that means they are totally, completely related to each other. So this is the square is actually a practical significance. It is the proportion of variability that is there. Let's move forward. Is we have already so those representations were showing you strong negative correlation. This is a strong negative correlation. If you talk about no correlation, here it is no correlation. Positive strong correlation. And then as you can see here, we say it to be a weak negative and a weak positive correlation. Try to figure it out yourself as to which one shows the weak negative correlation and a weak positive correlation. Here is another one of our data sets. So if you look at this data set, you are going to see, first of all, what do you think is the correlation? It is a negative correlation over here because as the x is increasing, the y is decreasing. But what is important to notice here is this data set. This data set is completely away from the spread of the other data set, and it is called what is an outlier. If you look at page number 63 of your book, it talks about the outliers. And so look at the expert, that is 3.25, and it says we examined the scatter plots to ensure that the relations were not attributable to one or a few outliers. There is group tendency that is not inflated by the extreme points. So this outlier may contribute towards the statistics or may not contribute towards the statistics, but it is very important to be transparent in a research and show that there is an outlier. You do not want the correlation coefficient to be understated or exaggerated in strength because of the outliers in those two relationships that you have. So that is one of those things that you want to keep in mind when you are doing your data set. So let's go and talk about the different types of correlations that is given in your book. One of the most common correlations that is used is the Pearson product moment correlation. If you do not see a correlation name mentioned, it is always the Pearson correlation that is mentioned. The Pearson correlation is you do not need to know the mathematics behind it, but you can see that it takes into account the standard deviation of the x-axis, the abscissa. This is like a tongue twister for me. Abscissa. Again, I'm so sorry for that tongue twisting. Standard deviation of the ordinate, which is the y-axis. It takes the covariance of both of them. That means how much of the variance of one is relating to the variance of the other, and then it is finding out the formula for the Pearson correlation coefficient. You are not going to be doing any of the mathematics with it, but it is really important to understand that each of the two variables in this case have to be quantitative. They have to be either interval or ratio, because those are the only ones. They have to be the raw scores. Those are the two important points to keep in mind, is the fact that two variables have to be quantitative and they have to be the raw scores. The symbol for is R. It is also sometimes called just Pearson. So, but if it is not mentioned, it is obviously the Pearson one. The next one is the Spearman's-Rojo, which is represented by RS, or here is the symbol. The difference between this correlation is that it looks at the rank order correlation. So if you have the data set, the raw data set, you are actually giving them a rank. So if you look at the height rank, my 73, the largest rank is 73, so that has got one rank. Then 70 is 2, and then 68 is 3, and then 4 and a 5. And then the weight is also ranked, and then I do the correlation between the ranks, which gives me the Spearman's-Rojo. This is also called the rank order correlation. So every one of them is converted to the ranks. That is where we come up with this. It also provides whether the two variables are correlated or not, and then the resulting. But it depends on the researcher as to what they want and their preference as to how they want to do it. Once again, both variables have to be quantitative, so that means it has to be a raw score, interval, or ratio. The next one is the Kendall's tau, which is very similar to the Spearman's-Rojo. But here, what the Kendall's tau does is, what if there is 3 or 4 people who have the same weight? So that means all of them would have the same tie. So it takes care into account the ties of the several tied data points. This is preferred over Spearman's-Rojo by many statistics people. There is an example given on page number 58 of your book, and your scores are 10, 9, 7, 7, 4, and 3. So if you look at the ranks that are being made, you have a 1, 2, 3.5, 3.5, 5, and a 6. So what it did was it gave a rank of a 3 and a 4, but then it found the average of those and gave them the same ranks. So this is where the difference is between the Spearman's-Rojo and the Kendall-Tau. Now, let's look at the other two. So these two are the point biserial and the biserial. So if you look at the point biserial and the biserial correlation, the biggest difference, okay, first let me say that these correlation are between a raw score and a dichotomous data set. When we say dichotomous data set is the fact that they have only two values, like male, female, yes, no. So when I look at point biserial, it is dichotomous is in true dichotomous. That means gender, male, female. There could only be two. There is no continuum in this. I could also say dead or alive. So that is a continuum. That is true dichotomous. They could be either dead, they could be either alive. You cannot have a person in between. Like, I'm not talking about a coma state, but that coma is alive, right? So dead or alive is true dichotomous. But in biserial, your dichotomous is an artificial dichotomous or forced dichotomy. In that, it means is, let's say, if you want to do a category in pass and fail, that is a dichotomous, right? But a pass and fail depends on what is my cutoff. I can make my cutoff to be 70%. So anything above 70% is pass, anything below 70% is fail. But in another case, it could be 60%. So it is not a natural dichotomy, but it is actually a forced one. It could also depend on, let's say, height. I want to say everybody who is above 5 feet is tall, everybody below 5 feet is short. Or this could be everybody above 6 feet. Or I could talk about anything that is not a true dichotomy is called to be an artificial or forced one. This is what is the biggest difference between the point biserial and the serial correlation. On page 59 and 60 of your book is where they talk about these things, is relationship between the height of the basketball player and whether they score any points. This bivariate relationship is between the two data sets, in which one of them is actually a nominal data set, a dichotomous data set. So that is where the big difference occurs in this, and it is symbolized by R. See, if you can look at it, R is always there. So if you only see an R, that is a Pearson's correlation. But if it has a subscript of the different subscript that we've been seeing is, but if it have a subscript of PB, that is point biserial, and then BIS is biserial. So the last one that we want to talk about is the Kramers V. The Kramers V is a unique one in which both variables are a nominal type, in which that means that it just shows us, measures the strength of relationship between the nominal variables. Most researchers do not use this often, but yes, there are researchers that have used this and it is statistically correct. So that is one of those things. So in summary, basically your ordinal scale, you have Spearman's and Kendall-Tau, but your interval and the ratio scale is your Pearson's product moment correlation. This is the most important one and it's the most commonly used correlation. Best of luck for this assignment. Let me know if you have any questions, guys. Don't forget to post on the course question discussion board.